This talk will be quite in line with the previous talk. We have done a similar composition study at AERA, at the Pierre Observatory. And I will explain something about that, but also add some other highlights that we have done at AERA. So at the Pierre Observatory, we have a radio array of about 17 square kilometers, which is located within the big array of 3,000 square kilometers of particle detectors overlooked by fluorescence detectors. So in this region, we have a really nice hybrid setup where we can do, where we see fluorescence, we see particles, we see radio, we have underground muon detectors. So we can do a lot of cross-checks there to see how our reconstruction performs. So the three things I want to quickly go over in this talk is that we have done measurements of the muon content in inclined air showers at AERA. This is sort of a precursor study for what we will be able to do with our future bigger radio array at the observatory, where we will cover the full 3,000 square kilometers. And part of that is also that we have looked into the stability of our radio signal, since we have about 10 years of data with our AERA detector. And then the main part of the talk will be about the mass composition, very similar to what Arthur just showed. So let's start with the muon deficit. So this morning, there was already an overview talk about this, that in measurements, we see more muons than in our simulations. This has been studied by looking at the muon and electromagnetic contents in the shower. And you can do this with water Cherenkov detectors and fluorescence, or with muon detectors and water Cherenkov detectors, but now also by getting the electromagnetic part from the radio. So this was work by Marvin Gottowik. What he did, he got the electromagnetic energy from the showers while having the particle detection from the water Cherenkov detectors, and then looked into what the muon content was there as function of energy. And in the plot on the top left, you see what this would look like for a pure iron or a pure proton composition, and the composition mix that has been measured by Auger. And we see there that also with the radio measurements, we have a quite large muon content there, more than you would expect from simulations. On the right, you see this in just normalized to the Monte Carlo, to the simulated expected muon content. And there you see sort of how many % you would be missing there. So for in the coming years, we will be taking data with the radio detector with the Auger prime part of the Pierre Observatory, and there this will be a major science case to investigate this with much larger statistics. I point you to the highlight to the talk in the parallel session this afternoon for more on this. An important part there is that we really know our radio signal well. So we have done some cross-checks by taking measurements from the galactic background, reconstructing it to our pipeline to extract the galactic signal only, and compare this to simulated, basically the radio sky, to see, to get an absolute calibration of our radio. So here you see the absolute calibration constant C as function of several years of data. And with that in red fitted a linear line to this. And what we see there is that within 1%, we can constrain that there is no evolution whatsoever. So there are no aging effects in our radio signal, which you would have with, for example, particle detectors or dust accumulation on fluorescence detector mirrors. So this can function in the future as a calibrator for hybrid detectors. So now on to the mass composition part. This part was already sort of explained that we have sensitivity to our primary particle by looking where the shower is maximally developed. Where it is maximally developed, you also have the most radio emission, and that is then reflected in the footprint we see on the ground. So by looking at this radio footprint, we can sort of derive what particles initiated those showers. So what we have done is we have taken the 7 years of data that we have at AERA, applied a very similar method that Arthur already described, where we do simulations for every measured event. We look for the best match with a parabola fit, do lots of cross checks, and try to do some bias corrections based on the simulations that we have, to then arrive at Xmax values for every shower. So on an event-by-event basis, we have investigated there any reconstruction bias, parameterizing this with our simulations. Unfortunately, I don't have the time to go into details here, but I will point you towards a link there with details, so you can look at that if you want. We have also used all these simulations that we have to look into the acceptance of our events. So do we have a bias-free data set? And also looking with those simulations in what is our resolution of this method. So we have done lots of cross-checks with looking into systematics. I will also leave it just here. Yeah. So the first part is the resolutions that we achieve. So LOFARP reported in a slightly lower energy range, an average resolution of about 20 grams. With AERA, we use a very similar method, and we also achieve here a very similar resolution, just at slightly higher energies. It is here shown as function of energy itself. We have slightly higher statistics, so we have been able to split it up easily. And what we see is that the highest energies, we are able to reach resolutions of better than 15 grams per square centimeter. So this is quite competitive with alternative methods like the fluorescence detection technique, basically our leading detection method for Xmax. So that is a very promising thing indeed. Second part is that for about 50 of our events, we've had this nice hybrid setup where we have fluorescence detection and radio detection. So we have been able to just one-to-one compare Xmax reconstructions. So you're not affected by any acceptance cuts where you need to, where you might have extra systematic uncertainties. You really can compare them one-to-one. And if we do that, that is what is shown in a histogram here. We find that we have no significant deviations between the two methods within an uncertainty of 4 plus or minus 11 grams. So this really limits how much uncertainty there can be between radio measurements and fluorescence measurements of the electromagnetic part of air showers. So this puts constraints on the actual shower physics going on there, while hadronic interactions are a little less understood. Electromagnetism is really well understood. So then on to the actual elongation rates of Xmax. So the distributions of Xmax represented in the mean of the distribution and the width of the distribution. What we show is that for the mean of the distributions, we are very well in agreement with the fluorescence detections. This is on a data set of about 600 showers that remain after our anti-bias cuts. Very similar method to LOFAR. What for us this shows is that we indeed see a quite light composition, exclude basically that it could be pure iron, but systematic uncertainties are still a bit high, and we have quite, compared to, for example, the fluorescence detector, much less events. For the second component of Xmax, we get also still compatible results. We also have a slight underfluctuation here, but there is nothing significant there within statistics. So that brings me to the results. So the take-home message I want to give you here is that radio is really now well developed. It has matured in the past 10 years, and we are able to achieve similar resolutions to fluorescence. We can get compatible results with them. So this is really now ready for the next stage of cosmic ray detection, especially now with the upcoming Auger prime radio detector, where we will also look into the composition of cosmic rays at the highest energies using the muon content. And we have been able to show with AERA now that this can really work over a long time scale, and we can also help narrow down uncertainties that we have for particle detection and fluorescence detection by limiting uncertainties by radio calibration for a hybrid detector. Thank you.